Hello, everybody. My name is Jonathan Sullivan, and let's go ahead and get started. A second, I'm going to bring the presentation up. All right, so today we're going to be looking at Markov decision processes, or MDPs for short. So these are broken down into basically two areas. We have the problem and we have the solution. So let's go ahead and look at the problem, and then we'll figure out how we state the problem, and then we'll move on to how we find out the solution, or at least given certain conditions, how we find out the solution. So we're going to start with the setting, look at what an agent is, what is the environment, how do they interact. So if we look at the interaction, we kind of have this weird graph here, but just remember that we initially start with the agent knowing nothing about the environment, or it may know something, but in our case, let's assume it knows nothing. It will then measure the state that it is in, or make an observation about the environment. And then based on that observation, it will choose the action to take in the environment. And then from there, it will receive a reward, and the next state is in. So it'll basically keep going in the loop of observing the state, choosing an action, observing the state and the reward for that state, and then choosing an action again. And we can just think of a state as a unique set of tokens that represent a unique configuration within the environment. So what is an agent? An agent can be a computer program that plays a game. It might be a self-driving car. It could be a walking robot, or it could even be a financial trading algorithm. And so the environments would just be what they interact with. So a game playing agent would interact with a game. A self-driving car would interact with the environment via sensors and LiDAR. A walking robot would obviously interact with the floor. They have to determine is there a step, is there a hill, an incline, and a trading algorithm would interact with markets and make decisions on whether to buy, whether to sell, whether to do nothing, and receive rewards from the market. So next we're going to move on to what a task is, and describe what the difference between an episodic task and a continual task is. So a task is an instance of a reinforcement learning problem, and as you can see, it just has state, action, reward, state, action, reward, and keeps going up, until it either ends. Till it ends in some terminal state, which is what we call an episodic task. Episodic tasks are tasks that have some terminal state, or just into perpetuity, and that's what we see with continuing tasks that don't have a terminal state. They just continue forever without end. All right, next let's look at reward and how we can tell if we reach our goals. What are goals and rewards? What is cumulative reward, and what is discounted return? So the reward hypothesis is basically saying that any reinforcement learning that we want to solve, the goals can be stated as the maximization of expected cumulative reward. That's a mouthful, but basically it's saying that our problems are really optimization problems. We're really trying to figure out how can we make this expected cumulative reward, or some scalar value, some number, how can we optimize to maximize that number? So here's an example here's an example that Google did, where they were trying to teach a robot to navigate different environments. And as you can see, the action is the force that's applied to the robot's joints. The states will be the position and velocity of the joints. measurements of the ground, contact sensor data, and the reward here is just a mapping from a state to a scalar value. That's all a reward is. And we can see in this case, they chose the reward to be this equation. And it looks kind of daunting at first, but if we look at it, the first part of the reward is the mean of how fast you're running straight to velocity in the x direction, and the maximum velocity that you can go. So it gets points for moving fast up to a point. Also here, this we lose a little bit of reward if we deviate, if we run in the directions that are not in front of us. So we will lose reward in that sense. And then here, this is basically controlling how much, how do I say it? How much we lose by going off track. So if we go to the left too much or to the right too much, we're going to lose some reward there. And then this term here represents the torque. So we could have a walking robot that satisfies all these conditions, but it does it in a way where it has to apply erratic movements, and that would be bad too. And then we have a 0.02 here, which basically incentivizes the robot to keep walking forever. As long as you can walk and don't enter your terminal state, you're going to keep getting a reward. And one thing to mention about reward, the way you define it really defines the behavior of your agent. What that thing they're trying to maximize or optimize for, that's all this reinforcement learning is trying to do. It's optimize for this value. So depending on how you define this value, you're also defining the behavior that you want your agent to learn. So let's look at reward and return. So we have cumulative reward here, denoted by G sub T. And cumulative reward, as we can see, is just the reward that you receive over the course of the entire task. And here we're denoting T as the current time. So here we have in blue, this would be the reward that you already gotten up until time step T. And these would be future rewards that you could calculate. Also, in the episodic case, this is just the sum of all rewards from T to the terminal state. In the continuing case, this is the just infinite sum, so a sum without end. However, as you see, I put a question mark there. There is a certain caveat here. So let's look at discounted return. We have this thing called a discount rate, always denoted by gamma, and it's just a number that's between 0 and 1 inclusive. So if you have a discount rate of 1, looking at this equation here, we can see that that kind of turns into this cumulative reward equation that we have up here. And that's by design. However, if we had 2 agents and they could pick an action that rewarded them 1, and they would pick the action that could reward them 0.5, for instance, and we computed the sum, infinite sum, in the continuing case with no discounting, then both of them will come out to equal to the same value. There'll be no incentive to choose a reward of 1 over a reward of 0.001 because they both are infinite. However, by applying a discount rate that is not 1, anything acceptable that is not 1, we are guaranteed to converge in the limit. So even if this thing is a, how do I say, infinite sum, we still can figure out a scalar value from the sum because it converges. And so that is the kind of tricky part about the continuing case. Either your task can have infinite episodes, or it can have a discount rate. I'm sorry. Either your task can have infinite time steps, or it can have a discount rate of 1, but not both. Never both. All right, so let's talk about MDPs and one-step dynamics. So here is kind of the whole enchilada. This is a definition of a finite MDP. So we talked about states. States are just ways to represent a unique location or configuration of an environment. We talked about actions. Actions are just functions of state. At the end of the day, we kind of want to say, hey, I observed this. This is what I need to do. We can also just think about them as being members of a action space or action set, if you will. Rewards, again, are scalar values that are functions of state. We can think about them also as functions of state action pairs or state action next state triples. However, no matter how you think about it, the math kind of works out. So I guess for the remainder of this period, we just think about reward as being a function of state. Next, we have discount rate, which we talked about. One other thing I forgot to mention. Discount rate actually tells you something very important in layman terms. It tells you how important the future is. So with a discount rate of 1, we're saying that that future value that I'm going to get 10,000 time steps off from now, that is just as important as the value that I can get the next time step. However, as you decrease that all the way down, let's say to 0, for instance, what you're then saying is, I don't care about anything in the future. I just want to know how do I maximize my immediate reward? What is going to be the biggest payoff right now? No long-term thinking. So as the discount rate gets higher, we think more long-term. As the discount rate gets lower, we think more short-term, or our agent thinks more short-term. All right, so we did discount rate. Policy. So we're going to probably talk about the solution in a second, but policy is here denoted by pi. It's just a function of state. Policy denoted by pi is a mapping which maps states to actions. So again, that's the goal for our agents say, hey, I'm in this game configuration, or I have a car here, a person there, which way should I turn? We want to map those states to particular actions intelligently. So that's what a policy does for us. And then one last thing to talk about is the Markovian property, or the way I like to think about it, history sucks. It doesn't, I like history, but in this case, let's pretend we're a rebellious history student. And we say the only thing that matters towards our future now is what's going on now. Things that happened in the past, things that happened 10 minutes ago, 5 seconds ago, 100 years ago, has no effect on our future reward. And that's basically what the Markovian property is telling us, that the future states that we enter doesn't depend on any other past states other than the present state that we are in right now. Oh, sorry, the highlighted part. So this is our one-step dynamic or transition function. And it basically says, well, there's 2 ways you can think about this. It can be deterministic or it can be stochastic. In the deterministic case, it's basically saying, given a state, given an action, what state am I going to end up in next? In a probabilistic case, or the stochastic case, to be given a state of action and a next state, what is the probability that that will happen when I take that action? I'm sorry, what is the probability that given the state and me taking an action as the agent, that I end up in this next state? And so, and if you think about it, we can always represent deterministic transition functions in terms of probabilistic transition functions, just by saying, this state action enter this state with a probability of 0, except for the case when it's the correct case, then we can say it equals 1. All right, so let's look at an example. Let's say we have this trash picking robot. It has 2 states, either high battery or low battery. There's an action space. So given a high battery, given the state of high battery, we could either choose the action search or the action wait. And given a state of low battery, we can choose the action search, the action wait, or the action recharge. And for this case, let's keep the math simple and use a discount rate of 1. So here is our example, MVP. We saw our state, we saw our state space, we saw our action space, we saw our discount rate. So we still need our transition functions, and we still need our rewards to state the problem. So here's our transition functions. And we can see, given that we're in a high state and we search, what's the probability that we return to that high state? That's going to be a 0.7 probability. And we can see that on the graph here also. That given a high state and I choose the search action with a 0.7 probability, we return to that high state. For 0.3 probability, we return to a low state. Yeah. So here we have also our reward functions. So given that we were in a high state and we searched and returned to a high state, we get a reward of 4. All right. All right. So what is the solution? And I think that is at time. So I will see you guys next time. If you have any questions, feel free to hit me on Slack or through Student Hub. All right, you guys. Y'all have a great night.